What's up, everybody? Going to talk to you very briefly about something called a Riemann sum, which is used to approximate definite integrals. I'm going to try and make this quick so you can mostly have time to work, but we're going to look at a few examples together. So the first thing we need to understand is what we mean when we're talking about a Riemann sum. So we talked briefly last class about this idea that if you are trying to integrate a function, you can represent that as the area underneath the curve. So maybe we have some magenta graph f of x right here, and we want to find a definite integral. So let's say we want to find the definite integral from 0 to 10 of f of x. In integral notation as there. Well, if we don't know an actual equation for the function f of x, we can approximate this definite integral using y values that we do know. So maybe we have some detail and we have some actual values right there. If I want to approximate this area, I can do so in a variety of ways. The common way is to use rectangles. So what I've drawn below is an example of a left Riemann sum of 6 equal subintervals. Now what that means, we refer to this as an L sum. You might also see it referred to as an L ram, a left Riemann approximation method, I believe. Okay, Google says I lied. A left-handed rectangular approximation method. I guess is what it stands for, but LSUM, LRAM, whatever you want to call it, it means this. It means starting from the very left of your interval, which for us is the x value of 0, starting there, go up to your graph and put the left vertex of a rectangle on the graph, and then draw your rectangle out to the right and back down to the x-axis. So my first little rectangle is this piece right there. And I could calculate that area by just using the formula for the area of a rectangle. Now notice the width of that rectangle is 2 and the height is 4, so the area is going to be 2 times 4 or 8. Now where that rectangle ended in terms of my x value, the next rectangle starts. So again, for the next rectangle, go up to the graph, put the left vertex on the graph, extend it over, and you've got yourself a rectangle. So I would calculate that area by going, again, the width is 2, and the height appears to be 6.5. So I could approximate that rectangle right there. So I would get 13 for that area. I continue to do this all the way up until where my integral notation tells me to stop, which is 10. So I can do the next one, go up to my graph, over and down. There it appears the width is still 2, the height looks like it is 8, so I would get 16 for that area. Next graph, again, x value that we ended on is now going to start. That height appears to be pretty close to the height from that 13 area, so probably about 6.5 again, so 2 times 6.5. And then finally, this last one, over and down. Again, width is 2. Height appears to be 3, so 2 times 3. And so I have all those areas. Now I drew that purple rectangle in on accident, but my integral is going from 0 to 10 from the x values, and so I should not include it in my calculation. Now, if you look at what we're dealing with, this is not a perfect system. There are gaps in the areas. If you look at this first little rectangle of 8, I don't have any of that pink graph right there. I don't have any of that pink graph right there. If you look at the next one, it looks like I have a little bit of extra stuff in the top right corner. And then if you look at the 13, I have a lot of extra stuff right there. And I have a little tiny bit of extra stuff right there as well. So, one way to look at it is that on some of the rectangles on the right, I'm getting too much I'm getting more than I should have. And on some of the rectangles on the left, I'm getting too little. I'm getting not enough. So maybe they can balance each other out a tiny bit. Either way, we could approximate this definite integral using that left sum, like we did, and adding up all those values. So, according to this left sum, with 1, 2, 3, 4, 5 rectangles of equal length, this definite integral is approximately 56. Now that's going to be totally different if I do a right sum.
Yeah, I don't remember the last thing I said. But anyways, that's an L sum.
If I wanted to do an R sum, let's look at a couple different things here. If I want to do an R sum, a right sum, a right rectangle approximation method, it's the same idea, except instead of putting the left vertex on the graph, you put the right vertex on the graph. And if you think about this problem with the missing area and the extra area, well, you could do some more subintervals. You could do skinnier rectangles and you get a better approximation. So imagine I did 10 subintervals instead. Each rectangle would be half the size, but maybe that would give me a better approximation. It's hard to say, but typically the more rectangles you could do, the better an approximation it's going to be. All right, let's say we're given a definite integral here from 0 to 4 of the function 1/2 x squared plus 3 dx, and we're told we want to approximate using an L sum with 4 equal subintervals. So if I'm doing 4 equal subintervals, then I'm going to end up with each rectangle being a width of 1, because I'm going from 0 to 4, and there are 4 equal pieces. So I can draw my rectangles in. If I'm doing a left sum, they're going to look like this. I keep messing that up. Boom, boom, boom. It's going to look something like that. Now, approximating this area, notice this is going to be an under approximation, but approximating this area, it's just a matter of finding the heights using our equation, 1/2 x squared plus 3. So my first rectangle has a height on our graph where the x value is 0. So if we plug in 0, we get a height of 3. So our first rectangle is just 3 times 1, the width. Add to that the next rectangle. Width is still 1, but the height, when the x value is 1, corresponds to 3.5. So I get 3.5 times 1 plus my next rectangle, where the height is 2, my y value is 5. So I get 5 times the width of 1, so I get 5. And then finally, when I do my last rectangle, notice that last height is 3. So I need to plug in 3 to my graph, and you get 3 squared divided by 2 plus 3, and you end up getting 7.5. So it's 7.5 times 1. So this definite integral, approximating this definite integral with an L sum of 4 equal subintervals, is a matter of adding all those up. 3, 3.5, 5, and 7.5 for a grand total of 19. Now, if I had chosen to do a different approximation, maybe I chose to do an R sum, like that. Boom, 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 boom. Notice that looks to be significantly more area. And whether or not it's more area or less area depends on the concavity of the graph. But you would calculate this in the same way, except my first height would be when the x value is 1. So my first height would be 3.5. And then my next height would be 5. And then my next height would be 7.5. And then my last height would be when x is 4 and my height is 11. So with an R sum, I would actually end up getting 27 as the value of that definite integral. So clearly, they're pretty significantly different. So maybe a good idea might be to average the two you get to get a better idea of that approximate area. So probably 23 is a little bit more accurate than either a left sum or a right sum. But either way, it's simply an approximation. But you might be asking yourself, why do we do this? Well, we've already talked about the relationship between position acceleration and velocity. Right? We know that if you take the derivative of position, you get velocity. Derivative of velocity, you get acceleration. But if you go the other way and go back up, if you integrate acceleration, you get velocity. If you integrate velocity, you get position. So a really big application of this is when you have data points from a velocity scenario of some sort. All right, so let's say we have this problem here. The velocity of an airplane in miles per hour is given below. Approximate the distance traveled using a midpoint sum in 3 equal subintervals for t in 0, that should say, to 6, like that. Okay, so what does this mean? We're taking a velocity function and we're using that to approximate how far it's traveled by calculating the definite integral. So we want the integral, just call it of f of x. Well, that's silly. Let's call it the integral of v of t. We want the integral of v of t from 0 to 6. We want to approximate that using 3 equal subintervals and a midpoint sum. So I think it's helpful to sketch a little graph of what's going on here. All right, so what I've done is I've just plotted each of the points essentially. And I want to do 3 equal subintervals from 0 to 6. So think about what that means. My first rectangle needs to go from 0 over to 2. My next one needs to go from 2 to 4. And my third one needs to go from 4 to 6. Now, it says I want to do this with a midpoint sum, which means not an L sum, not an R sum, so I'm not putting the left or the right vertex on the graph. I'm putting the midpoint of the top of the rectangle on that graph. So the height of my top rectangle is actually calculated from that middle value rather than from the left or the right. So my 3 rectangles are going to look like that. Now to calculate these 3 rectangles, I know the width of each is 2, so the first one is going to be 2 times that midpoint value at the time of 1, which is 175. My next one is going to be the width 2 times the midpoint value calculated at the t value of 3, which is 160. And my last one is going to be the midpoint value times 2, the midpoint value of time 5, which is 190. And I can calculate all of that and add it together to approximate the distance this plane has traveled as 1,050 miles. So that's a basic idea. There's L sums, there are R sums, there are M sums, and there are T sums, trapezoid sums. So now you will be working through a few problems, and you'll see what you can do. Good luck.